Welcome back. Last time talked about resolution for remote sense data, and resolution comes in more than one flavor for this type of data. So you have spatial resolution, how far apart, the minimum separation distance that allows you to distinguish between two objects. You have spectral resolution, which is how many bands are in your remote sensing device and how wide or how much wavelength each band encompasses. You have temporal resolution, and that is how frequent or how often you're able to capture the information. And you have radiometric resolution, and that's kind of how fine a scale you put to the energy that comes into your sensor. Do you go from 1 to 100 in units of 1 or 1 to 100 in units of 10? Okay, this time I need to talk a little bit about distortion. And so to set this up, you can imagine that you've got any of multiple ways of collecting your remote sense imagery of some object on the surface of the planet. But just like back in Module 3, I assume that was, when we talked about projections, with remote sensing, you've got a lot of distortion that can happen, and so you're going to have to correct for distortion. So remember, the energy comes into your electronics, and depending upon the wavelengths that your electronics are sensitive to, it puts out a voltage proportional to the amount of energy that's coming in. Okay, you can imagine a satellite up here orbiting the planet in a certain path and at a certain speed, and while that's happening, the planet is rotating underneath it. So you've got motion in this direction, say with the satellite, you've got motion in this direction with the Earth, and what ends up happening is you get these tiles that aren't oriented directly north-south, and you need to have overlap so that you can have be sure you have data in both of these tiles. And so you can imagine the remote sensor able to sense this area on the surface of the Earth, grab an image, and then it moves. The Earth and the satellite move, grab another image, and so each time you capture the image or the remotely sensed data, there's a little bit of overlap, and notice the directions are not due north-south or due east-west. With an airplane, you can see that similar things happen where you're flying your airplane and you're capturing images as you go, and you have overlap on the ends, and then when you turn around and come back in the other direction, you have side lap. So your images are not going to be perfectly distinct tiles, and so you're going to have to do a lot of correction there to make sure that stuff weaves together properly. Okay, there's this issue of oblique photography, and you can imagine that ideally when we're going to put something on a two-dimensional map, you want your photography to look as though it were photographed basically from an infinite distance, so that you're looking straight down on top of what it is that you're going to overlay on your map. But in general, you're not looking down from an infinite distance, and sometimes you can imagine that plane graphic from the last slide, sometimes you're coming in at an angle to the thing that you're taking a picture of. And so what you'll end up seeing is kind of the sides of what, when you're taking the picture from directly above, you wouldn't see. So depending upon the angle that you're taking the image from, you're going to get a different photograph. You're going to get an oblique photograph. So this involves geometric distortion, and this is a perspective view. You can imagine if we're not at infinity and we're capturing an image of two, say, skyscrapers, and this is where our remote sensing device sits, the skyscrapers are going to look like they're tilted out from this nadir point. Okay? If you were to take an orthographic view, which is the kind of thing we want to use in a map so we can overlay it on our other data that's projected, these things would look square and they would look straight because we're taking this picture basically from infinity. So you can see what happens when we're taking an oblique photograph. We're not going to get this nice footprint that's the vertical footprint of what we're taking. We're going to get pictures that includes the sides. So here's another graphic that kind of shows it. Here's an image that shows it. Our plane is coming in here and it's capturing information off to the side. That's going to make things look elliptical when they're off nadir, and they'll be circular if they're circular in true life. They'll be circular when they're on nadir, and they'll be elliptical when they're off axis. There's also terrain distortion, and that has to do with the fact that the image that you're taking is an image of objects that aren't all at a uniform elevation or a uniform distance from your sensor. And just like when you projected the three-dimensional Earth onto a two-dimensional map, you get distortion. And so it's the same kind of thing when you do projections as when you're doing remote sense imagery. You're going to have to correct for things that involve differences of elevation in the objects that you're capturing in your sensor. Okay, so say we have a sensor that's pointed straight down in the vertical. You could imagine ideally you would get squares that are nice and square. But what if that sensor is off axis and it's tilted? You can see that the size of the images that you're going to get are going to be distorted. So this tilt distortion not only applies in one direction, but you can imagine with a plane there's going to be three independent directions. So there's going to be three different types of tilt that you have to correct for: your yaw, your pitch, and your roll distortion. Lots of distortion. Okay, so how do you fix this? Well, you do what's called rectification. So what you're going to do is you're going to rectify all of these distortions as best you can. Here's an example of an image that's just an image, and this is actually a road, and you can imagine that this might be terrain with high spots and low spots and high spots. And so because of the difference in elevation of the things you're capturing an image of, this road, which is in real life straight, looks like this. When you orthorectify that image, you're able to get a road that's straight. And so you can imagine if you tried to overlay this on other information that included vector road features, it wouldn't overlay the true road features very well. But if you were to overlay this rectified image, you'd be able to do it properly. And so an image is just an image. An orthorectified image is something you can overlay on a map. You can imagine that there's a lot of geometry involved in this. It's not really complicated geometry in many aspects. You can imagine things you learned back in the days of geometry about similar triangles. There's all those rules you learned about similar triangles, but you have to apply that geometric correction to your image to get an orthorectified image. So what the heck is the difference? How does this boil down? You've got an aerial photograph, which has distortion. You've got an ortho photograph, which has, or at least attempts to, correct that distortion. Aerial photograph has a non-uniform scale. You can't use a ruler to measure on it. An ortho photograph has a uniform scale. You can't overlay or drape these things on vector stuff or on other images that are orthorectified because they're not going to overlay properly, but you can overlay an ortho photograph. An aerial photograph is just a photograph. An ortho photograph is a photo map. So in GIS, if you want to use aerial imagery or satellite imagery, you want to make sure that that has been orthorectified into an ortho photograph, and you'll be able to do the things you need to do in a map, like measure and overlay and drape. Okay, that was a quick trip through distortion. Just like with projection, you don't necessarily need to know the details of all the little pieces of distortion, but you do need to know that an image is distorted and it needs to be rectified before you can put it on your map with all the other things that have been rectified. Next time I'll spend a little bit of time talking about active remote sensing. So far we've been talking only about passive, which is where the sensor senses energy that bounces off the object. Generally it comes from the sun. The sun's energy bounces off the object and is sensed. Next time we're going to talk about active sensing, in which the sensor generates its own signal and then senses what comes back. So that'll be next time.